We're ready to consider a somewhat more complex example here that will combine the motion or the sliding down an incline with what we have seen from boxes and blocks with ropes on a pulley. We will have a glider A with a mass of 450 grams or 0.45 kilograms, sliding down a ramp with a coefficient of kinetic friction equal to zero point 0.1. The ramp makes an angle with a horizontal of 30 degrees. It is the glider A is attached to a rope, the other end of which is connected to a hanging block B with a mass of 15 grams. The rope is inelastic, of course, and goes over a massless and frictionless pulley. The question here will be to determine the acceleration of both objects and the tension in the rope. So let's start with the facts here, that the common things that we have seen in these questions of blocks and ropes and pulleys. The first thing is that because the rope is inelastic and massless, it effectively couples the motions of the two objects A and B, so they will have the same magnitude of the acceleration. The actual vectors for the acceleration will point in different directions, but the magnitude will be the same. The second very important point here in this type of examples is that because we're dealing with massless and frictionless pulley, the tension in the rope on both sides of the pulley will be the same. So I don't need to treat the tension along the rope on the one end and the other with different symbols and as different variables. When it comes to sliding down an incline, we did an example like that in the previous module. So if you don't remember that example, or if you feel like you need a refresher, just go back and watch that video. But in that video, we've determined that the best coordinate system, the most convenient coordinate system here, is one that is tilted so that its x-axis is aligned with the plane here of the slope, and the y-axis is perpendicular to the contact surface here between the block and the slope. That was the most convenient choice because that was the x-axis in this way was aligned with the vector for the acceleration of the sliding object, and the y-axis was aligned with the normal force exerted by the slope on the object. The only problem here was the gravitational force, which is directly downwards, always towards the center of the earth. So we had to split and work with its components gx and gy. For that reason, we worked with this angle here that I called theta between the vector for the gravitational force and the perpendicular, which turned out to be exactly equal to the angle between the incline and the horizontal ground. In this little red triangle, the adjacent side turned out to be the y component. So using trigonometric relations here, we saw that the y component had to be mg cosine theta with a minus because it points opposite to my choice for positive y. And the x component was the one that faces or is opposite to that angle in that right right angle triangle, and that was going to be plus mg sine theta. Again, if you don't remember how we derived those and how we got to those components, you can go back and watch the video on a block sliding down an incline ramp from the previous module. So let's complete here the free body diagram for the glider A. I will have a frictional force up the ramp. I will mark it as F friction, the vector for it, with components of minus mu Fn and 0. Remember, because the glider here is sliding, we're working with the kinetic friction, and the magnitude of the kinetic friction is always equal to a fraction of the magnitude for the normal force. How much is that fraction is given by the coefficient of kinetic friction, in this case mu. I also marked its component here, the x component, to be minus because it opposes my choice for positive direction to be down the slope. The last force missing from my free body diagram is the force to account for the interaction between the rope and the glider A. I will mark the vector as t. My diagram is getting a little bit busy, so I'm gonna write its components here where I have space The components of the tension, the vector for the tension are going to be plus t, that's the positive x component, and 0 because it's aligned along the x-axis of my coordinate system. I'm ready to apply Newton's second law for that object A. I'll start with the x components here. The gravitational x component is going to be ma g sine theta. Then I'm going to have the x component for the friction minus mu Fn. The normal force will have no x component, so I'm just going to skip the 0 and jump directly to the component for the tension, which is plus t. And that all has to be equal to the mass of the glider A times the the x component of its acceleration, which I have marked here as simply a. For the y components, the equation is going to be even simpler. There is no y component to the acceleration, so the sum of all y components of the forces they applied on that glider has to be equal to 0. So with that, I will have plus Fn, that's the y component of the normal force, minus mag cosine theta, that's the y component of the gravitational force, has to be equal to 0. So I see here I have an algebraic expression for what the normal force is going to be on that block or that glider. The normal force on it is going to be equal to mag cosine theta. With that, immediately I will know what the frictional force is, because the component for the frictional force is going to be mu Fn. So I can take this expression for Fn and substitute it for Fn in my top equation here for the x components. So I'm going to get plus ma g sine theta minus mu times Fn, which in this case is going to be ma g cosine theta, plus tension has to be equal to ma times the acceleration. So here's my first equation emerging from this dynamics analysis. Remember, the question of the problem is to find the acceleration and the tension. I have two unknowns and only one equation, so clearly I will have to keep going and writing more equations, or at least one more. So that equation will come actually from the analysis of the motion of the hanging block B. So here's the hanging block. I have moved it out of away from my diagram, which is busy anyway. So here's the hanging block with the rope attached to the top of it. I will choose a coordinate system with the y-axis up. Actually, I don't need x axis, so I'm just going to skip the axis. I'm just going to keep only one. The motion of B is one-dimensional. It might go up or down, but in no other direction. The vector for the gravity will point downwards. The vector for tension points upwards. The vector for the acceleration is downwards. Look at the original diagram. If the glider A is actually sliding down and to the right, we know that the hanging block B will be simply falling downwards with an acceleration a and vector pointing directly downwards. So Newton's second law for the block B is going to give me very simple equation here only for the y components. I have no other components. Minus mbg for the gravitational vector plus t, that's the y component for the tension vector, has to be equal to the mass of B times the y component of the a vector. Since the vector for the acceleration points downwards, remember its y component is going to be minus a. I have used the same symbol a as in the analysis of block A, simply because, remember, they couple. The rope connects the two blocks, and so even though the vectors for the accelerations will point in different directions, the magnitudes are going to be equal. Let me rearrange some of the terms here in this equation. I will have the tension has to be equal to the mass of B times G minus the mass of B times A. Or if you wish, we can factor out MB and write it as MB times G minus A. So this is my second equation. And the algebra is actually not so bad, because the second equation gives me direct algebraic expression for what the tension should be. So with that, I can go back to the equation that emerged from the analysis of the motion of block A and replace T there. So that equation will look now as plus mag sine theta minus mu mag cosine theta plus the tension, which I know from the equation just above, that it has to be equal to mbg minus mba, and everything has to be equal to ma times the acceleration a. I move all the terms with the unknown acceleration a to the right, and so that gives me ma sine theta minus mu ma cosine theta plus mb, everything multiplied by g, the acceleration due to gravity, has to be equal to the sum of two masses, ma plus mb, times the acceleration. So with that, I know what the acceleration should be. The, the magnitude of the acceleration should be ma sine theta minus mu ma cosine theta plus mb divided by ma plus mb multiplied by g. Let's open up some space here. I've kept the diagrams here, the free body diagrams with the components and the vectors, and I'm going to copy the equations of motions, the two equations that will give me the solution to this problem. The first one emerged from the dynamics analysis of the glider A, and the second one from the analysis of the hanging block B. Also, I already determined the algebraic expression that will give me the value for the magnitude of the acceleration A. And what is remaining here is just to plug in all the given that is the numeric values given in the problem, and perform the calculations to find out that the numeric value for the magnitude of the acceleration of both objects to be 5.89 meters per second squared. The second question about the tension will come actually from us going back again to those equations of motion. The second equation seems simpler to me, so that will be my preference to use it. So I'll have tension is going to be equal to the mass of B times the difference between G and A. I already know A. The value of A is 5.89 meters per second squared, so I can just plug it in here and find a numeric value for the tension in newtons. The mass of B is 15 grams. I've switched here to kilograms, 0.015, and then that has to multiply the difference between 9.8, the value of G, and 5.89, that's the value for my acceleration. So that gives me for the tension to be 0.05865 newtons. I kept an extra digit. I'm always reluctant to round when I get the last digit equal to 5, but here it is if you want to get the answer in the standard 3-digit notation. I switched even to the scientific notation here because the number came out too small. The tension in this problem will be 5.87 10 to the minus 2 newtons.